All right, looks like it's about time. Thank you all for joining us today. It's my pleasure to introduce Michael Olinick from Middlebury College. He's presenting using an arms race model to illustrate key concepts and techniques in a first differential equations course. Thank you, Michael.
Thank you, and thank you to the organizers for inviting me to do this presentation. So my goal is to try to illustrate how we can use a fairly simple model at various points in a first introductory differential equations course to illustrate a lot of the basic techniques and concepts that come up in that course. The model is motivated by a pretty large question: what causes nations to wage war? This is a question that has certainly perplexed many people over many generations. And one of those persons was Lewis Richardson. Richardson was a physicist and mathematician, best known for his work in meteorology. He was a Quaker, very much opposed to war. And during the First World War, World War I, he served as a volunteer ambulance driver in Europe and saw firsthand the carnage and violence of war, and became very interested in understanding how wars emerge and what he might do to help turn the world's attention towards this problem and ways of alleviating it. What Richardson noticed through a fairly detailed study of lots of conflicts in past centuries was that the existence of large military supplies, weapons, and manpower often increased the likelihood of violent conflict, and that nations which did not have a large amount of destructive weapons were often able to settle disputes by other means. And so Richardson saw that there was a link between the outbreak of war and the stockpilings of arms, and premised this notion that if nations were both increasing expenditures and defense budgets, a small spark could start a major conflagration, as what happened in Europe in World War I. Whereas when nations were decreasing defense budgets, small incidents did not trigger war. And he wanted to build a model that would examine what conditions exist that would predict whether arms races were stable or unstable. And he developed a model now known as Richardson Arms Race Model. It describes the dynamics of arms expenditures of two nations. Each one is fundamentally driven to increase its arms by fear of what the potential opponent is doing, but also has internal resistance to artificially high levels of arms expenditures. And Richardson also noted that there can be factors that are independent of the level of arms, which actually contribute to whether those expenditures are increasing or decreasing. So the fundamental model is a mutual fear model. We're positing that these nations are not aggressive, do not see themselves as aggressive, but realize that if there is a potential enemy, we have to be well armed to deter any attack on ourselves. So the mutual fear model has, as you see, the pair of differential equations, x prime equals ay, y prime equals bx, where the coefficients are assumed to be positive constants. We then add to the model these internal constraints, which say that the rate of change of my expenditures is negatively affected by how much I'm already spending. It becomes harder and harder to raise an arms budget that is already very high because the society has other needs that it needs to fulfill. And then Richardson added a third term to represent factors that could contribute to increasing or decreasing arms expenditures that were independent of the levels. So this is a fairly simple linear model. And the constants R and S could be positive or negative, reflecting some underlying good or ill will towards the other nation. So just to review briefly this model, X and Y represent arms expenditures changing over time. Our coefficients A, M, B, and N are assuming positive. R and S are constants of an arbitrary sign. And our differentiation is with respect to T. So at the beginning of a differential equations course, this is a good model to illustrate the benefits of doing a phase plane analysis that can reveal lots of different possibilities for the dynamics of such an arms race. And all students need to understand in terms of this kind of analysis is that a derivative is a measure of a rate of change, and a positive derivative implies that a quantity increases, while a negative derivative would indicate a decrease in the quantity. So if we look at the first equation, say for the blue nation, and we could ask the natural question of where is there some stability? Where is the rate of change equal to 0? And that's easy to see. It's just the straight line whose slope is m over a. And that line divides the plane into two regions. Above the line, our x prime is positive, so x would increase over time if we're at such a point, whereas if we're below that line, we would see a movement to the left because x prime would be less than 0. And we could do a similar analysis looking at the null line for the red nation. And here again, the straight line along which the derivative is 0, a so-called stable line for the red nation. Any point along that line is a point at which the red nation would not have an incentive to increase or decrease. But above the line, y prime is negative, so we'd be moving down. Below it, it is moving up. So note that in this case, as actually with the blue nation as well, that if we're at a stable point for a particular nation and we get pushed off that line, the model says we attempt to move back toward it. So if we get pushed below, we'll see y increasing. If we get pushed above, we'll see y decreasing. So each nation is attempting to restore stability in this model. And that's the first kind of interesting interpretation we get out of this model. Now, if we put these two null lines together, so here's a typical way they might be represented, and look at where we have movement to the left, right, up, or down, we see there are 4 regions. If we begin in this region, we have both derivatives decreasing, so we be moving downward towards the left. And if we're in this region, here we'll be moving in a southeast direction towards the stable point. Starting in this region, we move towards the stable point, and starting here, we move towards the stable point. So no matter where we begin, over time, we approach this point of stability, equilibrium point for the system, where both derivatives are 0, and we would have an arms race which reached the constant, approaching a constant level over time. However, we could have a different configuration. So here's a slightly different picture of how these two null lines might cross. And here, if we look at motion up, down, right, and left, we see different behaviors in these 4 regions. If we begin in this zone, we have positive derivatives for both terms that continue to be positive. So we will be moving up and to the east. This is a mutually escalating arms race. If we begin down in this region, both derivatives are zero, and we move toward mutual disarmament. If we begin in a region over here, for example, then there are a couple of different possibilities as we move towards the northwest. We could cross the blue line first, in which case we wind up in this zone. So we would see a motion that looks like this. On the other hand, if we begin at a point down here in this region, as we move northwesterly, we might cross the red line first, and then we have mutual disarmament. So this is a highly unstable arms race. Similar things happen if we start here. We either wind up in this zone or in this zone. So the outcome here depends a lot on where we start. What are the initial conditions? It's a blown up picture. It looks like this. So one of the questions that students might ask is, if we start out in one of these ambiguous zones, we know that for some points we wind up in mutual disarmament. For other starting points, we wind up in mutually escalating arms race. Is there some dividing line so that if we're above that line, initially we will move into the region of mutual escalation. And if we're below that line, would we move down here? And how would we find such a line? Well, the characterization of the line would be dividing between the two. There might be a starting point which actually carries us over time towards that stable point. And that would say the direction of motion, which is given by dy dx, is the same as the slope of the line connecting us from where we are to the point x, s, y as the stable point. From our model, our dy dx term is y prime over x prime. And so we have this system, which students can solve. And we wind up with actually a quadratic equation, which gives us two slopes. Actually, one that goes through the stable line in these two regions, and another that looks like this green line. These will turn out, students will discover in the middle of the course, are just the directions of the two eigenvectors for the system. But we can tell quite a bit. So the next point in a course, we might have students use some software, give them some particular arms race with different coefficients, and ask them to explore what's the long-term behavior in this situation. On this side, we have the stable arms race, and here we have one of these unstable ones. So we can also ask, well, what characterizes the difference between a stable situation as depicted on the left and an unstable situation on the right? And one thing that students will notice or conjecture is that one difference between these two pictures is on the left, the blue line has a greater slope than the red, and it's just the opposite on the other side. The slope of the stable line here, L, for the blue country is greater than the stable line for the red country. And we know what those slopes are from the differential equations. And so we have the condition that Mn is greater than AB. And you can think about this in terms of an interpretation that A and B are these coefficients of mutual fear. And somehow if we combine those by looking at the product, if that's smaller than these internal constraint coefficients, we have stability. And we have the opposite inequalities in the case of an unstable arms race. We can actually even find for students early in a differential equations course, you can actually look at the pure mutual fear model of Richardson's initial preliminary step, we can solve that differential equation by separating the variables. So it's a good example of a model where separation of variables becomes actually a useful solution technique. So here's a pair of explicit equations on the left that gives us a stable solution and an unstable one. We can look at other configuration of these null clines. Perhaps they don't intersect in the first quadrant, but intersect somewhere else, or perhaps they're parallel, or that they, in fact, we just have the same line twice. These are interesting projects for students to carry out on their own. Other students I've had have been looking at extensions to a three-nation model in various configurations of relative hostility of two of them against the third. So good example that some of my students have looked at are the relationships between the United States, Russia, and China, each of whom is looking warily at the other two. And there's, of course, relation of these models with the Lanchester combat models that can also be explored. When we get to the middle of the course, where students in a differential equations course are actually beginning to look at linear systems and looking at the matrix of coefficients for the system, they would look at the characteristic polynomial and notice that the constant term here is this mn minus ab term. The eigenvalues here, students can see that they're actually going to be unequal, and both are going to be real in this particular case. And at least one of them is negative. They both might be negative in the case of the stable arms race. So here we've beginning again with the same pair of models that we've looked at just using some software to generate a typical set of trajectories. We can actually solve them explicitly using the eigenvector eigenvalue analysis. A good place to generalize from here is, instead of assuming that we just have constant terms here, we could think about having a pair of continuous functions. Provides a good motivation for introducing variation of parameters techniques for coming up with a formulation for what a solution of such a system might look like. And we could, of course, change the coefficients in these matrices to functions of time rather than just as constants. Or they could be, instead of functions of time, they might be coefficients that actually depend on what the arms level expenditures are of the two countries. Of course, these are now highly nonlinear systems. So students would presumably start applying some numerical solution techniques, which is usually covered kind of towards the end of an introductory course. And they can go in a whole lot of different directions, exploring a lot of different individualized or group projects on their own. In an advanced ODE course, this would be a good model to introduce delay differential equations. The original Richardson model is assuming that each nation can immediately adjust its expenditures based on what it's spending and what its potential enemy is spending. But typically there's going to be some time lapse that it takes a while to change the legislation to increase or decrease the military budget, so that the rates of change at any particular time are actually dependent on what the arms levels expenditures were sometime in the past. So although this is a relatively simple model, it's one that confronts an important real-world problem and also gives us a lot of motivation to introduce the important topics in the first differential equations course. So thank you for listening. I'd be happy to take any questions or comments. So, any questions?
I'm sure I have a question. Do you ever talk about how you would figure out what the parameters are?
Yes, it certainly, in a modeling course, I would spend a lot of time on that. And I would talk about how Richardson himself attempted to assign parameters based on information that he had about how the nations of Europe rearmed after World War I, and what are some of the flaws in his approach. There are a number of studies also where people have attempted to look at other arms races to see how well a Richardson model might actually fit real world data. Doesn't do very well looking at the Cold War era, just looking at the US and the Soviet Union. It does better if you take a little broader view and look at NATO versus the Warsaw Pact. And it fits best probably in terms of actual data, the arms buildup between Iran and Iraq in the 1970s and 80s. But I usually don't have time to do that part in the differential equations course. Other comments or questions? Beverly, yeah.
I learned about this model about 50 years ago from Bob Borelli and Courtney Coleman, who started ODE. And it's interesting to think that that was in yes, it was Cold War, but it was a relatively peaceful time compared with what we are now. And I haven't seen that model for the last 20 or 30 years. So I'm glad you're coming back to it. I think that's really going to be important. Thank you.
There is a fairly extensive literature with more advanced, more complicated models that attempt to be more realistic.
I think there's a question in the chat.
Oh, okay. Go to the chat. Okay, so constants R and S. So if we can go back to the.
Why am I not seeing the chat?
Yeah. So if R is positive, that's going to contribute to making X prime larger. So this would be assumption that there's an underlying hostility between the two nations, or at least how X perceives Y. And if it was negative, that would of course tend to a smaller value for X prime. So there might be some amount of goodwill that balances out some development of arms on the two sides. So if you were to think, for example, of the US and Canada as the two nations, there's a tremendous amount of underlying goodwill between the two countries, and certainly a much smaller coefficient of fear of what the other one is doing. I hope that addresses the question. I'm happy to take any other comments or questions. I'll just leave this open until everyone is left.
Thank you.